Hello, and welcome to the latest edition of Our Future in Space. I'm your host, Dr. Jeff Greenblatt. I'm the Vice President for Science and Research at Orbital Assembly Corporation. And in this podcast, we explore the technical, economic, social, political, and ethical considerations of moving large numbers of people into space to work, live, and ultimately to thrive. Our species is at an inflection point in its evolution where we now have the ability to sustain human life in low Earth orbit for long periods of time and soon throughout other destinations in the solar system. This is happening for several reasons because of the dramatically falling cost of launch, the significant advances in computational capability, the commercialization of low Earth orbit, as well as a growing awareness that our species is starting to exhaust the resources on Earth, and that some new solutions, frankly, are needed that are going to include space. Do we merely survive on this small planet, or do we branch outward into the solar system and thrive? And not just for a few dozen pioneers, but millions of people working and living in space. I'm here with my co-host, Eric Ward, who's the Vice President for Engineering Design at OAC. How's it going, Eric?
Oh, it's going very well. I'm excited about our interview. Today, we've got Professor Akhil Rao from Middlebury College in Vermont, where he teaches economics, focusing on statistics and space economics. His research is focused around the common use and property rights of orbital paths. Thank you for joining us. Maybe you could tell us a little bit about your research.
Yeah, thanks for having me here. It's great to be here. So my research, like you said, focuses mostly on orbital paths, and I think one way to think about this is low Earth orbit is a shared space that we all use. It is a finite space. It's big, but it's still finite. And in any shared finite space that humans use, there are some questions you can ask about how do we allocate space to different users, and how do we allocate space to different uses. One of those uses, perhaps, that we have been allocating maybe too much space to is orbital debris. We've been allocating a lot of space to just kind of hold this debris that we're leaving there. And that's maybe not the best use of that space. So my research focuses on using tools from environmental economics, thinking about Pigouvian taxes, property rights schemes, not necessarily to implement those in orbital space, but to use those as a lens to think about how we can use orbital space more efficiently to generate more value for humans wherever they may be from that resource.
Wow, you've certainly brought up a couple of very interesting topics already, and I don't know all the terms you've just used. So do you want to, like, what is it?
Yeah, sorry.
Pigouvian tax? What did you call it?
Yeah, I'll unpack that a little bit here. So in economics, there's many different kinds of taxes that we think about, and one in particular that economists, I think, across the board, but especially environmental economists really like, is something we call a Pigouvian tax, after Arthur Pigou, an economist in the early 1900s. The idea of a Pigouvian tax is that when you are polluting a shared resource, or when you're creating congestion, when you're in some way harming other users, but not internalizing that harm in your decision-making, something needs to get you to internalize that harm in your decision-making, so that as you're thinking, do I maybe throw this, I don't know, plastic bottle away or not? You've got something there that kind of makes you think, hang on a second, if I throw this plastic bottle away, that's got all these different costs on local ecosystems, on people who've got to clean it up, on all kinds of things. And so what we typically do in economics is we try to figure out the right price to get you to internalize that properly. And so we call these types of taxes Pigouvian taxes, after Arthur Pigou, because he was kind of the one who paved the way for this kind of thinking.
Gotcha. Okay, so this sounds a little bit like so my background, for those who don't know, is partly in, environmental protection and particularly climate change mitigation. And so we have this concept in that field that's, we just call environmental externalities.
Yeah, exactly.
And it sounds like it's really the same principle, just by a different name, right?
It's exactly the same principle. And in fact, the right level of the Pigouvian tax is exactly the damage is caused by those environmental externalities. And so if you've thought at all about carbon taxes, or think that they might be an effective solution or not, you've thought a lot about Pigouvian taxes, because a carbon tax is a Pigouvian tax for the environmental externality of carbon dioxide production.
Right. Okay, so all right, so that's yeah. Go ahead, Eric. Jump in.
Well, yeah. So I mean, this is a topic that's important to Jeff and I. You know, one thing we do at Our Future in Space is really try to look into, you know, this natural progression of humans into space, but it's this brand new territory, and how do we, as we transition there, how do we do it better? How do we, you know, be better stewards of our civilization and our environment as we go into space? And it seems like this is, you know, kind of right along that line. And so we understand what a Pigouvian tax is. You know, how does that apply to space? How does that apply to humanity in space? And how can we use concepts like these to kind of improve the way that we you know, expand out into space?
Yeah, those are great questions. So I'll try to go in order roughly here. I think the way to think about this for orbital space is to think about what are the consequences of leaving debris or inactive satellites or fragments, however you want to classify this. What are the consequences of leaving that up there? And one of the really salient consequences is that we create collision risk for other active satellites. So imagine that you've got an active satellite. It's providing some really beneficial services. Maybe it's taking really useful pictures of the Earth so that you can monitor climate systems, for example. And you know, it's operating in a very cluttered environment, and stuff in space in orbit is going really fast. And you know, those collisions that it might have with some of that junk left behind could end its mission. It could be catastrophic for that satellite. And so,
And just to jump in, Akhil, sorry, for those who will be listening later on the audio only version, we have an image here of orbital debris objects, you know, in various orbits around the Earth. And could you just briefly describe what that looks like?
yeah. So if you look at this picture, or if you visualize this picture in your mind, in the audio version here, we've got the Earth in the center, and there's kind of a fuzzy layer surrounding it, very close, and that's low Earth orbit. And that fuzzy layer is reflecting that there's a lot of debris in low Earth orbit. And then there's kind of a dense cloud, I would say, of stuff as you go further and further out, with a really pronounced ring around the Earth where the geostationary belt is. And if you kind of squint and look hard at this picture, you'll start to see little patterns emerging. And those patterns reflect the different orbital paths that people have found very valuable to put satellites in or to use for some kind of space exploration. And so the distribution of debris around the Earth really reflects the distribution of where we as humans have found value in placing satellites.
I see. Right. So already we can see that those things that are most valuable without any other kind of structures or limitations are just going to get congested and naturally become a problem at some point, right?
That's exactly right. And so this is where I think mechanisms like a Pigouvian tax come in. And so, you know, this collision risk from these objects in orbit is a real problem to these active satellites. That's the environmental externality. And so if we were to calculate the damages caused by a collision, so you can think about, you know, it's going to produce a bunch of fragments because the satellite gets hit by something going real fast and it breaks apart. It's going to lose the services that the satellite provides. If somebody finds those services valuable, they're going to have to fund a replacement. We can take all of those monetary damages and weight them by the probability that they occur. And then we can use that to calculate, you know, here is the expected cost that an operator is incurring by being here. We can do that same calculation to figure out here's the expected cost that an operator is imposing on others, or that a satellite or a piece of debris is imposing on others. And from there, we can figure out here's the kind of dollar amount or euro amount, whatever, of this tax that you ought to be keeping in mind as you're making this decision of, do I put my stuff up there? Do I try to fund a debris removal project or not? You should be really thinking about this dollar amount of damages that you're imposing on others if you do this, I guess, without maybe full thought.
So you're not necessarily recommending a policy per se. You're just kind of interested in what is the cost, you know, what is the cost of doing business in space in these various orbits, and then leaving it to policymakers and others to say, well, we should charge everybody a user fee, or let's fund a program that will reduce the risk and pay for it somehow with these user fees, right? I mean, is that kind of where you're going with it?
Something like that. Yeah, I mean, like if you ask an economist what's the optimal policy, we'll probably have something that we think is great, but that policymakers might not think is so great. And so I do think that I call it an orbital use fee a fee levied on all objects in orbit as long as they're there. I think that would be a great policy, but maybe that's not politically feasible. Maybe there's other constraints that are outside of just the dollars and cents of this. And so if that's the case, then that's the case. And policymakers can navigate their way towards something else that is good. But I think what I'd like to do is really clarify, these are the things that are good, and here's why they're good, and here's exactly how good they are. And, try to navigate your way towards these things rather than other things.
So, all right. So I guess what I'd love is, do you have an order of magnitude estimate at this point for what the cost, per year, let's say, of being in an orbit might be, or are you not there yet?
So we have, I think, order of magnitude estimates that are, I think, about probably the best estimates that you could get right now. There's a pretty substantial data challenge in monetizing some of these costs. We've got really good physical data on what's there comparatively, but much less good economic data about how valuable is this thing. And part of the challenge is that some of these values that we have are not really reflected in any market prices, right? Like, what's the value of better climate monitoring, and where do you find that dollar figure listed on someone's balance sheet to price that in?
I see. In other words, it's more than just the cost to the company to build and launch another satellite. It's sort of all the indirect benefits.
That's right.
Depend on it. Yeah.
Yeah. And so when we look at mostly the quantified costs, so excluding some of these unquantified costs, as yet unquantified, about the benefits of climate monitoring and so forth, we get to a figure of roughly $14,000 per satellite per year now. And that figure rises somewhere between 10 to 14% per year to reflect kind of the increasing scarcity value of clean orbital space over time. Yeah. Now, that figure, I should put this in context, right? Because satellites are very heterogeneous, and this is like one average figure calculated across all types of satellites.
Right.
That figure, if you look at kind of the average satellite that we constructed that from, that's about 0.1% of the profits per year from a satellite. And so if you've got a commercial satellite, about 1/10 of your profits is the number right now, but that number escalates over time.
Yeah.
Right.
Yeah. I mean,
that sounds like a really good.
Oh, I'll just add one more thing about this. These taxes, these profits that the orbital use fee would tax, increase the value of using orbital space. And so by reducing collision risk, they are actually increasing the value of the sector. It's just a little bit, I think, difficult to think about, I'm getting taxed, how is that putting money back into my pocket? But in this case, it is, because there's just this deadweight loss of all this junk up there that the tax is helping to realign incentives and get people to treat differently.
Yeah, I think that's really interesting. My thought, and we talked about this a little bit, about the policymakers versus the economic correctness, right? Is like something like this orbital use fee, right, would require coordination across all spacefaring companies, right? Every nation and company that's going up there. So it's kind of an interesting point to make, I think, that the orbital use fee, if it's being aligning incentives, and then maybe that money is being applied to something like debris removal, you can kind of get into a game theoretic situation where, regardless of the law, it is the correct decision to pay these fees and support that activity.
Right. Like even voluntarily, like people would take out insurance or pay into some, collective orbital debris program, even if they're not required to, Eric, you're saying?
Yeah. I guess if the math works out in a way, that the kind of that game theory, application, you look at what you can do, what other people are doing, and you get into a situation. I don't know how prisoner's dilemma-y this is, or maybe tragedy of the commons you'd get into, where if everybody else is being good stewards of the space, you don't have to be a good steward of it, and you'll still reap that benefit. But if nobody's being good stewards of space, it sucks for everybody. And so
that's kind of where we're at now.
Yeah.
Right.
Yeah.
we're being like quasi good stewards, but then every now and then somebody does something really, unfortunate that affects the whole.
Mm-hmm.
Yeah, that's right. And Eric, to your point, that's exactly right. There is sort of a game theoretic a struggle underneath the hood of trying to make this work. I have some really recent work with a Middlebury student, actually, Aditya Jain, who's graduating this year, going off to UChicago Energy Lab. He's doing great stuff. But we have some game theoretic work actually examining exactly this. What happens if we have these countries doing different regulatory things, some of them more environmentally friendly than others, and they're trying to eventually work their way towards a treaty to remove debris from space. And what we find is that there does exist a really nice equilibrium where everybody agrees to levy these regulations. Maybe it's not harmonized, maybe it's not ideal, but there does exist a way to make the math work so that everybody's going to find it in their best interest to do this. And that actually makes it more likely that we get to a debris removal treaty. And so this is, like I said, it's pretty new work, but it's very exciting to me because it shows that there is maybe a win-win way to make this work.
Yeah, I would certainly hope so, because I mean, in my view, and I'm sure you guys agree, is if we don't fix this problem in the near term, it's going to be very difficult to access Earth orbits, let alone orbits that are not connected to the Earth, right? Cis-lunar space, interplanetary space, because you just can't get out. In fact, it reminds me of this crazy scene from the movie WALL-E about 20 years ago. I'm dating myself, but maybe both of you have seen it, or certainly some of our viewers may have, where, it's a future dystopia. Most of the humans have left, and only WALL-E, who's this little cleanup robot, is left to kind of like tend the garbage heaps that are left. And at some point he gets off the planet through an unfortunate set of circumstances, I guess. And so the moment is he's rocketing off into space, and suddenly he like has to plunge through this debris field in low Earth orbit, which they illustrate rather cartoon-like, right? Just bang into things like pots and pans. But the point is that it's like completely covered, right? Because we were so irresponsible. We don't want to be there.
No.
Yeah.
Very, very much not. Yeah. So what is one way, and I guess this is more on the policy side, but we had a viewer ask a question, if we had these orbital use fees, and let's say we have, like you said, some treaties in place, maybe they're not perfect and harmonized, but we're able to convince the public that, this is the correct solution. This is the, game theoretically optimal thing. And we don't use those words because I found that people don't like it when I say, well, it's game theoretically optimal. But it's more of a math thing for us nerds. But say we convince everyone that we need to have these treaties. How would something like that be in place? Like, is this the sort of thing that a launch provider would pay every launch and they'd pass that on to their customers? Is this something that the FCC would have to deal with when they talk about all? I mean, we have these treaties on communication and different different communication bands. Is that something that kind of would be lumped in with the other aspects of current space flight, or do you think we need some new mechanism to put in an orbital use fee?
So we certainly could use a new mechanism. There's a world where I think that could be a very nice outcome if we can do that, but I don't think it's strictly necessary to have a new mechanism. And I think that your comment about the FCC, that's kind of the direction that I'm thinking of. Maybe not the FCC per se, but I think that this. So let me back up a second here. The environmental externality, the problem here is collision risk. Collision risk is not created by launches per se. It's created by the things that launches are putting into space. And so I think the right place to levy the tax is on the things in space, because that's what's causing the problem. That's where we should alter the incentives. And so this would, I think, ideally be something that could be implemented by an entity like the FCC as a condition for market access to the US market, for example. So here's one way this could work. You can take sort of the fee amount that an object ought to pay. You can look at the market that object serves, or the population that it serves, and you can allocate that cost to those populations differently. Now, those populations live in different parts of the world. Let's say that you were talking about something that is serving the United States in large part, right? A communication satellite, perhaps. So that satellite, in order to provide service to the US, it needs to get a bunch of regulatory approvals right now. This is how it works right now. You got to get like FCC approval for spectrum so that you can access the US. Well, the minimal path that I could see to getting this orbital use fee in place would be to say, look, in addition to getting FCC regulatory approval, as long as you want to be serving the US market, you've got to pay this proportion of your external cost as an orbital use fee to the FCC. Now, if you want to serve more and more of the world, you've got to pay other people those costs as a condition for market access. And so this way, you know, maybe launch providers work this into their pricing right away. Maybe it takes some time. But this way, if you are using the satellite, if you are operating the satellite, your incentives are immediately altered to reflect some of the externalities that you're creating for other folks.
Yeah, I mean, it kind of incentivizes you to get more responsible with your own satellite operations, right? Because if you let a satellite go derelict, then it becomes a hazard to others, or if you start ejecting things off of it for whatever reason, or let alone blow it up. So I can see how the fees would be, you know, both to sort of, I don't know. I mean, I guess there would be like a punishment mechanism too, in case somebody is a bad steward and then they get fined, right?
Right.
You know, in proportion to what damage has been done, but but the fee is kind of like keeping people on good behavior, and also they're getting access to a cleaner environment, directly or indirectly.
Right. Yeah. And there's a third thing that this fee does too. That's actually I think really beneficial, which is that it creates a demand, it creates a market for debris removal services. Right now, debris removal is a difficult proposition. It's a difficult business to be in because, you know, this stuff that's up there, like, why would someone want to pay to remove that? It's not costing them anything now, but removal will cost them something. You know, they've got to have a pretty strong altruistic motive, or, you know, be a constellation, for example, that needs to dispose of their debris for their own constellation's benefit in order to be willing to pay that. And so now with this fee, we can create this incentive to say, look, if I want to stop incurring this fee, I need to pull my satellite down. Well, the fee is $1,000. I'm willing to pay up to $1,000 for somebody to pull this down.
So, I mean, that I think is a really interesting point, right? That there's that disposal at the end of life that, you know, traditionally hasn't been very, you know, very well thought out outside of GEO, of course. But like, there's a lot of debris up there now. There could be an accident, right? Let's, you know, say something hits something and it, you know, destroys a satellite, and which I believe actually we had a case of that recently. If I recall, a Chinese and a Russian satellite, you know, just ended up hitting each other. You know, maybe that's not built in this fee structure, right? It's some unplanned accident, right? Or maybe there's, you know, a fine if you're not proactive about being safe about that. But there's debris in there. How does that kind of factor into this, right? You know, beyond, you know, finding a company that intentionally creates debris, you know, is there mechanisms that we can incentivize or pay for the removal of debris that's already up there, or that arises from an accident?
Yeah. So there's maybe two ways to think about this, right? One is that, like, if I follow sort of the Pigouvian tax logic very rigorously to its conclusion, then the answer would be that the orbital use fee amount jumps for everybody who's in those regions immediately after that accident. Because even though they didn't cause that accident, the background risk is higher. And so the probability that they will have a collision that creates more damages is higher. And that fee has to reflect that. But to mechanisms that can dispose of debris that's already up there, I mean, this is very much a question. And I think that there's almost no way to do that without making somebody pay for it now. And I think that that's going to be painful for somebody somewhere, presumably.
Yeah. That's really interesting. So I wanted to pivot a little bit. I know there's a lot of interesting economic stuff when we're talking about a civilization off the planet. I want to get to that, but first I had a quick question. A couple of years ago, you and I were talking about exactly how big space actually is, right? Like it's huge. But if I recall correctly, you were doing some research on the actual utility of different orbits and the fact that there is some limit to how much stuff you can put in different places. I wanted you to talk a little bit about that, and maybe we can think about, obviously around the Earth is very important, but this is a sort of question that we're going to have further and further as we go into the solar system. How big is space actually, and why are there limits, and what are they?
Yeah, so to the question of how big is space actually, I don't think I have a very good answer here. I'm going to defer to the astrophysicists and those folks on this. But to the question of why do we run into limits, that I think I can answer, right? And my sort of really crude analogy here is like the American West, right? The American West is huge. There's a ton of landmass there, but like there is still traffic in Los Angeles. And if you were to think about this as like the American West is huge, why is there traffic in Los Angeles? Like if you do the sort of rough math of, square miles per person, like there should be no traffic, but there is. And the reason there is because people's value from using certain areas is really correlated, right? Like I get a lot of benefit out of going to a juice store, and maybe you also get benefit out of going to the Jamba Juice. And so we're going to both be going to the Jamba Juice, and that's going to create some congestion. And so that's why we're going to be running into limits in pretty much any gravity well that we operate in at sufficient scale. It's just the things that are really valuable to us, to me, tend to be not that dissimilar from the things that are very valuable to you, in a way that means that eventually you and I are going to find ourselves having to figure out this allocation problem of, well, how much of this space can I use and how much of this space can you use, and go from there.
Right. And I thought you were going to bring up the idea that some orbits or some locations, let's say, because we're not just talking orbits, we're talking hard,
like
planetary
points.
And moon. Yeah, Lagrange points, which I guess technically are orbits, but yeah, being the moon, Mars, various other points. Some are more valuable than others, right? Like the permanently shadowed craters, one of my favorite topics. The moon currently a hot place. I mean, cold place, but it's hot in terms of lots of people want to go there, set up shop there, both for research as well as manufacturing, commercial. And so I guess you're saying a similar, that's where you're going to congestion, places where people want to go, which of course can change over time, right?
That's right. That's exactly right.
So what you're saying is that if we had, I don't know, 1 trillion people, one day, like you're saying, they wouldn't all spread out evenly throughout the solar system. They would be clustered. And what drives that clustering is really maybe the question, right?
Yes. And I think that there's a lot to be discussed there about what drives that clustering. But I think, and in a very fundamental sense, it's similar to the question of why do cities exist? If there was no reason to cluster, we wouldn't have cities, but we do have cities, and that's a pretty robust feature of kind of humanity that we like to gather in places. And so I think that we'll see clustering in space, even with 1 trillion people throughout the solar system.
And that makes sense. And that's not necessarily a concern, right? Cities provide a lot of value to our society, and
that's right.
We've gotten pretty good at making cities, and there are benefits and minuses of every city, right? Like the traffic in LA, for example. And but that's not necessarily a problem, right? That we're clustering in places,
right?
At least as individuals. Does it become problematic when we're talking about in particular economic activity? I mean, besides just the availability of resources, does congestion locations kind of factor into how a spacefaring economy might work?
I think it does, but I think it goes in both directions, actually, right? So agglomeration, that's the term we use in economics for people coming together to generate more value. Agglomeration provides real benefits, like you said, with cities, right? And so you can think about this in sort of rough cost terms, that like if our houses are next to each other, it's really low cost for us to like hang out and maybe do cool things together. But if our houses are very far apart, then we've got to pay this travel cost, right? Like in time and resources to do that. And that cost is going to reduce the amount of cool stuff we do together. And so,
which is a problem, because I really like hanging out and doing cool stuff.
That's right.
Most people do.
Yeah, you know, it might make it harder, in fact, to do epic stuff, right? Looking at
Yeah.
your background there, Eric.
Yeah.
And so I think it's not a problem. I think it's actually a good thing that we would cluster, because space
Yeah.
is, like you said, I don't know exactly how big it is, but it's pretty darn big. And like, once you get to that size, if we've got to spend a month getting back and forth, like, we're just not going to do a lot of stuff.
Yeah.
that way.
Well, and actually I was going to bring up an image of the solar system just to give people some sense of scale. So I'll do that now. But, you know, so this is actually on a log scale. So, you know, the outer solar system is much further apart from everything from each other than the inner, but this kind of puts it on a proportional scale. And I guess if time is roughly equal to distance, yeah, travel times are getting longer and longer. Go ahead, Eric.
So yeah, so Earth is at 1 AU, right, which is defined as an astronomical unit, which is by definition the distance of Earth to the sun, right? And so for scale, if you take our pictures off the bottom, so I can make sure I get the numbers right, you're looking at, from the sun out to Jupiter is 5 AU, right? To Mars is like 1.5, 1.7. You've got a big asteroid belt in between Mars and Jupiter, right? And so there's the distance from Earth to the sun, and then you've got, you know, 3 or 4 times that distance going outwards from Mars to Jupiter.
Right. Yeah, and then beyond. So.
And then beyond, of course, yeah. But then, you know, there are those interesting points, right? The asteroid belts with with their resources, you could go beyond Jupiter, but there might not be the ISRU there that you'd need, that you could get from the main belt asteroids. Or we mentioned Lagrange points, which for our listeners, those are stable orbits in between 2 celestial bodies. So you could have like the Earth Moon Lagrange points. There are 5 of them. One's in between the 2 bodies, one's on either side of each body, and then there's sort of a trailing orbit and a leading orbit. But those are interesting specific points, right, where you could have a stable agglomeration, right, a city of spacefaring activity in these stable orbits. But you might not necessarily have that, you know, in this, you know, random spot in between Jupiter and Saturn, for example.
That's right. That's exactly right.
Yeah. So what else? I mean, in terms of take homes, like, I mean, we could probably spend a lot of time just discussing this graph, which is partly why I wanted to bring it up, but I don't want to bore our listeners either. So yeah, like, are there a couple of high level take homes you might pull from this diagram, Akhil?
Yeah, I mean, I think one thing that I would pull from this is that, like, I mean, your point about distance and time, I think, is a really good one. I would add another point that, like, distance on Earth is roughly proportional to cost to travel, or, you know, you can think about that sort of, each additional kilometer or mile that I travel adds some amount of cost.
Yeah.
In space, it's a bit weird because of the gravity wells, and so, you know, getting from Earth to Leo is energetically much costlier than traveling that exact same number of miles from, say, the moon to outwards in some direction. And that energy cost is going to mean that there will probably be settlements, habitats, places where people are living broadly, right, that are not so deep in a gravity well that you're going to be paying a lot of gravity-related energy costs to go up and down. Probably not so far out that you're really far away from where other humans live, but somewhere in between, where the energy cost of going back and forth of battling gravity is low, but you're still close to the Earth, certainly, and or close to other places where humans live. And so I can imagine a world in which, a future in which we kind of slowly expand outwards from the Earth, but we would probably see people still choosing to locate in places where there's not too much gravity.
Right. I mean, because it makes it energetically much easier. So then it's cheaper, right? So it's and that means people will move around more if it's cheap to do so. But there is the time element around space travel too that is very hard to get around. I mean, there are some interesting ideas out there. We interviewed Jeff Grayson a few weeks back, and he was talking about very fast interplanetary travel, but it's still kind of a concept at this point, not anything proven, on the development timeline. So yeah, what would you say as far as the time element of moving around the solar system?
I mean, I think one thing, actually, I do have maybe one useful economic thing to say here. And I think it's that when we've been thinking about what are the paths that people will take, for example, to get from the Earth to Mars, I think there's a lot of focus on these minimum energy transfer orbits, right? So these are orbits that you take a path from around the Earth to around Mars, and it minimizes the amount of energy that you have to use to get there. And the trouble with those kinds of paths is that they also result in very, very large travel times, very slow trips. And, time is money in some sense. There's a time value of money. $1 today is not the same as $1 tomorrow. And so I think we'll probably see people focusing on transportation pathways that are not minimum energy orbits, and they won't be minimum time orbits either, because the absolute fastest you could go would involve tremendous energy cost. And so we'll probably see something in between. Right. So, you might not want to spend all that time, because you'd probably be willing to trade some of that time in exchange for a little bit higher cost to get there sooner. But you're probably also not going to be burning the candle at both ends, so to speak, here.
And just one follow-up question. So I've struggled with this a lot as I've imagined people living in different parts of the solar system. I've shared some of this with you, Akhil, as you know. I think there's a big difference between being patient about shipping non-living objects around the solar system, like rock, refined metals, propellant, things like that, versus people, right? I mean, people's time in some sense is a lot more valuable. Plus, you have to keep them alive for longer if you're taking 3 months to get from, I don't know, one asteroid to another. Whereas you can wait a couple of years as long as you've got the pipeline full. If you're just like shipping lots of, more aluminum bar, and it just kind of keeps coming, right? So I guess, so you have any reflections on that distinction?
I mean, I think you're exactly right about the distinction, right? I think that if it's something perishable, and humans are certainly perishable, that time becomes much more expensive than the energy. And there's some point where the cost of energy is no longer less than the cost of time. And, maybe humans are perishable, but, you don't want to spend $1 billion per person to get them from point A to point B. You'll accept a lower cost in exchange for slightly longer time. But for non-perishables, like, absolutely, you can just fill up that pipeline and let it take whatever time it takes and save your money that way. And so I guess to the extent that we see automated extraction from asteroids, I would expect to see more use of minimum energy transfer orbits. And to the extent that we have human centric extraction with people actually there doing stuff, I'd expect to see more things that use more than the minimum amount of energy.
Yeah, totally agree.
So I wanted to ask, so this is of interest to me, at least. Jeff and Akhil, you guys co-authored a study on building a 1,000 person Mars city for, I think it was for the Mars Society in 2019. And it was a great paper. You guys explore both the economic and political elements of such a city. And I'm hoping that that you can share some of the highlights there.
I mean, so I want to initially say, I guess, that there's a ton of really, I found, interesting kind of chemical discussion and engineering discussion of like how you would actually build things there, and like where do the abundances come from and where are the scarce elements, and I think Jeff is the person to speak to that more than I am. But on the economic and the political side, I think that like one of the things that got me at least really excited about this is that it's not that there's no law in space. There is space law that is an established body of practice. There's a bunch of things that you got to think about there, but there isn't a lot of, I guess, social inertia in the kinds of social systems that you can build up there. And so there are some, I think, really radical ideas that may be good on Earth, but would be very, very hard to implement here because we have a lot of social inertia that you could implement on a new Mars city. that I think would be consistent with international law as it exists now, and also align incentives towards producing more value. One of those systems that I think is really interesting is it comes from a paper written by Glenn Weil and Anthony Lee Jung called Depreciating Licenses. And the idea here is to move away from a view that you own property or that you own access to some resource indefinitely. Because if you do have that, then it gets very hard to incentivize people to turn over the resource to another user who may have a more socially valuable use case. When that comes up, you get into what economists call the holdout problem, where, you know, if you've got the one tract of land that is needed to build a railway line and everybody else has sold, like you've got a lot of leverage, and you have a strong incentive to exploit that leverage to extract as much as you can from the railway company. And, you know, maybe that's good for you, but it does reduce the number of socially beneficial railway lines that get constructed, and that's not good for society. And so the idea that we had here was to take Weil and Jung's depreciating licenses scheme, which says that, you know, you own the use of this resource for now, but every year you've got to put up an estimate of the value that you think that resource is. And you put up that estimate and you pay a small fee proportional to that estimate. And, you know, if you're happy with that, that's great. Well, you might think, I'm just going to say that this is worth very little, so I pay very little in fees. The catch here is that if somebody else thinks, hey, I could use that plot for something really great, or I could use that resource for something even better, they look at the estimate you put up, and if they can match that estimate and they have the resources to do that, then you have to transfer it to them. And so that kind of pushes you in the other direction of, well, you know, I want to reflect a higher estimate so that, you know, I don't have people just take my stuff. And, you know, when you combine these two forces, the place where you want to be is you want to give an estimate that is actually the value that you derive from this good, because anything less, and you're increasing the chance that somebody takes it from you when you still have value, anything more, and you're increasing your fee burden. And so there's that sweet spot that the incentives work in opposite directions to push you towards.
And I guess if you have like an auction, you know, or any sort of healthy, you know, market with enough participants, you'll quickly come to the actual, or very close to the actual economic value of using that resource, right? At least that's the hope.
That's right. That's the hope. Yeah.
So yeah, no, so we incorporated this into our paper, which was very cool. I really loved having Akhil's sort of, you know, orthogonal thinking to what I was focused on, which was like, you know, extracting oxygen and metals and things like that. But I think one thing that we struggled with was how often should this turnover happen, right? I mean, yearly seems kind of mismatched to the way space is currently being thought of as being developed, right? It takes like a decade to develop even a single spacecraft, let alone like harvesting materials from a solid body. So any guidance or thoughts on how often somebody should be able to hold a license before taking it up for auction?
No, that's a great question. I don't know for space, and I think that this is one of the interesting questions that I think researchers will have to try to pin down. So Michael Castle-Miller, and Jeff, I think you and I have both worked with Michael on this. He has this idea of a lunar development cooperative that takes a similar kind of depreciating license structure to sites and access to services on the lunar surface. And thinking there, I think what we concluded was that initially, at least, you want to give people like 30, 40 years to figure out what they're going to do, because it takes so long to build in space. And then after that, you want to slowly increase the frequency of these turnovers. And I don't think we were ever thinking about something like 1 year turnovers in certainly not in the next 20, 30, 40 years. But, you know, eventually, I think the goal would be to get to something like 5-year turnovers or something like that. So you can kind of balance the need for time to do stuff with the sort of value of having some creative disruption.
Yeah, I think that makes sense. And I think that, you know, regulating bodies as well as the participants themselves would quickly figure out what seems like a fair turnover point. So yeah, but the main point is you're essentially, I mean, you're doing something quite radical. You're essentially redefining what it means to occupy land. You're taking away a true ownership structure and making it more like perpetual rent, where
That's right.
everything would be held by some designated body with authority to, you know, to hand out leases, right?
That's right. And well, there's an interesting wrinkle here. So international space law, people seem to be converging to an interpretation, or seem to have been at an interpretation that says you can't actually own land on the moon. You can't actually own a parcel in space. And so this constraint was sort of the fundamental constraint that got me thinking about, well, if we're going to keep international law as it is, we got to have some way to allocate stuff, to allocate positions. So what do we do here? And the Lunar Development Cooperative idea is one of the things I really like about it, is that it doesn't require ownership of the land. Nobody has to own any land anywhere on the moon. What it does is it says that this LDC, this cooperative, is going to provide services like electricity, like, I don't know, transportation, rocket pads, whatever, at a site. And in order to get those services, you got to be current on your fees, and you got to be participating in the system. And if you don't, then you lose those services. And if you want to pay the huge fixed costs of building out all those services yourself, more power to you, but you're probably going to have a much easier time of it if you just go with the system and take advantage of the services that are there.
Yeah, and this, I mean, just as an aside, you know, this could become real very quickly, because we now have several, you know, entities, both private companies as well as government organizations like NASA and ESA, and China and the China National Space Agency, all wanting to build permanent lunar bases, right? Possibly in the same region, probably not on top of each other, but nearby, right? In the South Pole region and maybe elsewhere. And so, yeah, I mean, how are we going to allocate who gets to use what and how long they can stay and everything? Like, it's going to be relevant real soon.
Right.
So I was just going to bring up a graphic here from our paper, Akhil, showing, I mean, this was somewhat arbitrary, but we decided to locate this 1,000-person town somewhere in the northern mid latitude. So just giving people an idea, like we chose a real place, and you know, in the northern hemisphere of Mars, it would be kind of near other resources, but not so close that it would be like on top of a mountain. Anyway, you weren't involved in this part of it, but I just wanted to give people a graphic idea of where we were.
I know in that paper you talked about a little bit about economic bootstrap growth. You know, we're talking about a city of 1,000 people. Right now we have 0 cities of 0 people on Mars. You know, how does an economy for a city like that kind of grow?
Yeah, so the way that we thought about bootstrap growth here, I think, is it's one way. There are many other ways that one could construct, but I think this is one way that's reasonable. Was in the context of what is known in economics as the solo growth model. So that's solo like Han Solo, but with a W at the end. And so the solo model, the idea here is that you have a fixed savings rate. And so let's say that you have some people and some machines, right? So labor and capital, these are the two kind of fundamental inputs here. And you can use labor and capital to produce stuff. And that stuff that you produce, you can consume it, and that's great. But you can also save some of that value, and you can reinvest that value. You can reinvest that value into accumulating more capital and into kind of supporting more labor. Now, if you hold the amount of labor that you have there fixed, so you don't add more people for a little while, but you keep accumulating capital, then you can keep increasing the amount of stuff that each person, each unit of labor, each hour of labor can produce. And that can very quickly, you know, initially there will be much bigger returns to each unit of capital that you put down than later on. And that's kind of standard diminishing marginal return stories here. But that can let you very quickly build up a lot of output per person, a lot of capital per person, which you can then use to support an expansion of the number of people there without having living standards decline too much. And if you just kind of keep going through these cycles of building up capital, improving your output capacity, saving that, using that to build up your labor stock a bit more, then reinvesting some of that output in more capital, et cetera, you can start to, bootstrap it, right? You still need some initial investment, but that way you can use some of the surplus generated there itself.
mean, it sounds similar to how I think a lot of us in the space industry are thinking about these initial investments.
Mhm.
You know, right now we're bringing everything with us to do one-off missions, but we're quickly turning to this idea, like with the lunar base that I just mentioned, that you bring a long-lived resource that is then something everybody can use, and then you build upon that. Once you have power, you can then put a, I don't know, you can put a habitat, and then once you have a habitat, now you can have some uh, rudimentary processing facilities, and then you bring a large rover, and then you have a second habitat, and people can, support that. So it's a similar idea, but you're sort of thinking of from a purely economic perspective. Don't
That's right.
don't sort of consume everything that you produce, but invest in the future.
That's right. That's exactly right. Yeah.
Mm-hmm. Yeah, it seems very wise. Well, so I was going to ask one more sort of open-ended question. Eric, did you have anything else you wanted to ask about this Mars city?
Oh, I have so much I want to ask about everything, but we want to keep the timeline reasonable here. So why don't you go for it?
Okay, well, so yeah, maybe we'll revisit this Mars City question some other time, because I do want to say, like, a lot of our conversations, have been about orbital colonies, orbital cities, which I think there's a bright future for that, but it's certainly not the only way. And certain individuals are very keen on making surface settlements, and we want to include that in that conversation too. So I think all those are valid conversation topics. So Akhil, you said something to me when we were preparing for this interview that really struck me as far as timelines. And you said, and I'm going to see if I can quote you, you see that space development is going to be strongly driven by environmental protection in the next 30 years. And then certain things are going to happen that is going to make space development even more important after that. And I was just wondering if I captured that right, and if you could elaborate on that idea.
Yeah. No, I think that's pretty much right. Like I would add error bars on that timeline in one direction more than the other, right? So I would say maybe 30 to 70 years, 30 to 50 years. That's kind of the range where I think it's going to start really either heating up or cooling off very rapidly once we get there. And so what I'm thinking of when I say environmental protection will drive space use, there's these surveys that NASA has been doing of the American public to see what about space does the American public value. And pretty consistently, Earth observation, monitoring climate systems shows up as like #1 priority. That's the thing that people value from space a lot. And I think that's probably a really good, a really good way to build out trust in this approach, right? So there's a lot of people, I think, who are skeptical of space exploration and space development on the grounds that we have a lot of problems on Earth. And I think that in order to win over more people and ultimately make space exploration and space development something that everybody can see a future in, we really have to do a much better job or continue to do the work of making the case that this stuff benefits people on Earth right now. And the way that we do that is, it seems, with environmental protection and monitoring as kind of the central mission focus, right? And so there's a lot of ways that you can think about that. You can think about, for example, as we've discussed, Jeff, moving heavy, dirty production off planet. And the real value there is not just that you've taken a bunch of emissions off planet and into orbital space where there are fewer people, but also that you have freed up a bunch more land on Earth to provide ecosystem services, to provide habitat for animals and other wildlife that promotes biodiversity, to provide water filtration, air filtration, all these services that the ecosystem gives us. And that's a big benefit. And now, as we look into the next 30 years, the reason I'm thinking about that timeline is that climate change is pretty urgent right now. And, if we can kind of get our act together as a species over the next 30 years and start making the investments that we need to prevent sort of some of the worst climate outcomes, keep bending that temperature, that greenhouse gas curve downwards, then in 30 years, I think we're going to find ourselves with the capacity to do more in space with the infrastructure already prepared and less of a need to focus on environmental protection and more of a capacity, I guess, really, to focus on expansion. And if we don't, then it's hard for me to see a world where we're able to marshal public support for big public investment programs in getting off planet beyond sort of continuing the environmental monitoring and protection mission.
Right. So you're saying that between now and 30, roughly 30 to 70, such a range, right? But between now and the end of the century, let's say,
yeah,
middle to the end, you're saying that we should continue to make investments in space infrastructure and technology, but that we're kind of waiting to really accelerate until we've got our environmental issues under control here on Earth. Is that a way of paraphrasing that?
I think that's exactly right. And I don't think this is a necessary condition to doing space exploration and development. It is certainly possible that we could have very wealthy individuals and companies, for example, choosing to just go ahead and do stuff. But I think that as time goes forward, as we go through the next 30 years, they're going to find it increasingly difficult to be very profitable doing that, or to, do that without a lot of public pushback. And so I think that really prioritizing the environmental mission, really making it clear that, we have these mechanisms for, sharing the surplus that we generate from space with all humans, right? So if we take a polluting factory off Earth, well, one way that goes is that there's a bunch of people on Earth who don't have jobs, and that's not a recipe for something politically sustainable. And so you got to have mechanisms as well to say, look, the resources from this surplus that we're producing, you're going to get some of that. You're going to have a stake in seeing this grow. And that's a way that we make sure that humans on Earth continue to see value in space exploration. And I think that that's a really productive way forward, because public investment, there's very little that can match that scale. I guess even the richest person on Earth still has wealth dwarfed by the Department of Defense's annual spend, right? Like,
oh, sure.
There's just orders of magnitude difference between what individuals and corporations can do versus what governments can do. And to get governments bought in, I think we have to get people bought in.
Yeah, jobs is part of it. Yeah, I mean, I will say that if you think about areas for growth, like software was a big growth area, 10, 20 years over the last couple of decades, and where you still see a lot of investment in new companies forming. But I guess there's murmurs that, like, where is the next growth wave going to come from, right? And a number of people are pointing towards space and saying, there's a lot of potential for growth, unlimited resources, and therefore jobs. Even if most of those jobs are still on Earth, building satellites or operating things remotely from the ground, right? So it's less expensive. But it strikes me that if you have a growing activity in space, it will help to fuel growth, and that could be one way in which the benefits of space come back to the ground. But I think you're thinking a little beyond that, sort of direct dividends or something.
Yeah, that's right. I mean, I think those dividends are a critical part of the story, right? Yeah, I guess just to restate this, like, the climate timeline, I think, is its own thing that imposes pressures that we should be taking very seriously.
Yeah, I really like how you're weaving environmentalism and climate change concern directly in with your space, economic modeling framework. I mean, I think the two are completely intermixed, and if anything, the space industry sometimes gets pushback from folks who are like, you're completely ignoring our problems and maybe just trying to escape from them. What's going on, right? And you're seeing this more as a win-win. I mean, invest because it's kind of our future, but make the investment mostly about fixing our problems on Earth, today.
Right.
Very nice.
Yeah.
Well, okay.
Yeah, I think we're running out of time here. So just wanted to give you a chance. Anything else, Akhil, that you'd like to tell our listeners, before we cut off that we didn't get a chance to talk about already?
I don't think I have anything new. I guess just maybe a call, I guess, for optimism here and excitement, right? That, like, space is really exciting for the physical resources and opportunities that it can provide access to. But I think it's also really exciting because this is a setting where we can start to really radically envision new futures, new ways of organizing society, and our economic activities here. And that's something we should be very excited about, right? It's alarming because we could go in some very maybe unhappy for humanity directions, but it's also exciting that we could go into totally radical good for humanity directions. And
yeah,
I'd like that maybe to think about the upside. Yeah,
I love it. No, that's a big reason that Jeff and I are doing this at all, that, we really think that not only is this, almost a necessary, inevitable future as, as us a part of nature, these creatures that expand and grow. We're also looking at it as how can we think about this problem or the future of humanity in space in an optimistic way, and what can we do now to kind of help us move in that direction? So I really appreciate that call for optimism. That's wonderful. So I guess we're going to wrap up here, but thank you so much for coming on and talking with us. It was great having you, and I'd love to really dive into things like what an economy on Mars might look like at some point as well. So maybe we'll get a chance to have you back in the future. But thank you very much for joining us. And to our listeners, thank you guys for listening and watching. If you're watching live on YouTube or watching later, we really appreciate it. Hope you found this to be an interesting conversation. And if you want to, reach out to us, you have additional questions for our speakers, for us, suggestions on future topics, go ahead and shoot us an email, ourfutureinspace@orbitalassembly.com. You can also find us on Twitter @OurFutureSpace and Facebook @OurFutureInSpace. So thank you so much for listening, and again, Akhil, we really appreciate it.
Thank you. This was a lot of fun.
Great, we enjoyed it. All right, everyone. Until next time. Take care.